All right, everybody, thank you for attending my talk about areostationary satellites and eclipses. If you don't know what that means, that's perfectly fine because I'm going to tell you what it means. I really appreciate you again coming out here just to hear me blab a little bit about my thesis. And we're going to jump right into it, actually. First, we want to just get a quick baseline comparison of the differences between our good old buddy here, Mars, and our good old friend that we know and love, Earth. This is not to scale, obviously, but we can tell, first of all, that Mars is further. If you don't know what semi-major axis means, that's fine for now. Just know it's the distance from the sun in very broad layman terms. So Mars is further. The eccentricity of the orbit, which basically means how elliptical it is. If you don't know what that means, that's okay. I'll explain it later. Is higher. The orbital period is nearly twice. So one Earth year is, or sorry, 2 Earth years is nearly 1 Martian year. Mass is slightly lower from Mars compared to Earth. The radius is about half of Earth. The surface gravity is about a third. So if you weigh 100 pounds on Earth, you'd weigh 30 on Mars. It's a great way to lose weight. In terms of Earth itself, we got, of course, about 24 hours a day for Earth, and it's a little bit over 24 for Mars. Earth has, of course, the one moon we know, and Mars has two moons. Phobos and Deimos are little asteroids. And the obliquity is 23 and 25 degrees. You will learn what that will mean in a bit. Let's talk about how to describe an orbit. Many of you may already know what the Kepler elements are, but you may not know all of them. So first two I want to mention really quickly, this is for your 2D case. You got your semi-major axis and eccentricity. Your semi-major axis is the half of the major axis line. What's the major axis? That is the line that lines in the plane of the two foci. So on the top right, you can actually see it's labeled A. That's your semi-major axis. That's the best way to describe sort of the radius of an ellipse since it changes based on your position. Eccentricity simply describes how elliptical it is. You have your inclination. This is the deviation of the orbital plane from the central body's equator. You have the right ascension of the ascending node, or RAN, which I'll call it. This rotates the orbit depending in the plane of the equator of the central body, depending on the value. You have your argument periapsis. This rotates the orbit in the plane of the orbit itself. And of course, you have true anomaly. All this does is just simply describe the position of the satellite measured from the periapsis in degrees. Now, this may not make sense, which is okay. It's a bunch of words. I'd like to show you visually what it means. I made this. It's amazing. We can see here the true anomaly in orange. We can see the ascending node, the inclination, the argument periapsis, the periapsis itself. And periapsis, by the way, just means the furthest point in the orbit. Closest point in the orbit. Apoapsis is the furthest point. And the first point of Aries is just a way to measure off for many of the orbital elements. Now, what I really want to explain in detail, actually, is areostationary satellites. And this is really important. This is the whole motivation for the thesis, if you could say. Mars has always been a goal and target for the first human steps. We've been there since 1997, Sojourner. We've always had a constant presence on Mars, but a constant presence needs a constant need for communication. And regardless whether it's a wheel trail or footsteps, there needs to be a foundational network of communicative satellites, just like we have here on Earth. It can be used for communication, like I just said, weather observing, or a sort of relay system. This is where the areostationary satellite comes in. So it's analogous to an Earth geostationary satellite. What does that mean? Let me just draw it out real quick. So you have a semi-major axis value of 20,420 kilometers, rounded up to the nearest number. The main benefit of a geostationary aerostationary satellite is that the orbital period is actually the same speed, it's the same amount as the side rotational period of Mars. So as Mars orbits, as the satellite orbits Mars, it's going to match its rotational speed. Fun fact, Areo is derived from Ares, the Greek god of war, and counterpart to Roman god of war Mars. But the main way it stays stationary in the sky is due to the small inclination eccentricity. If that weren't true, you'd have an areosynchronous orbit. What's an areosynchronous orbit? Again, like I said, the orbital period matches the rotation, but it's any inclination or eccentricity. Or sorry, any inclination, just inclination. Aerostationary is when you have that near zero inclination eccentricity. So when you look up to the sky, that thing's not going to move depending where it's at. And all aerostationary orbits are asynchronous, but not every asynchronous orbit is aerostationary. Okay. Let's talk about a little fun, complicated thing called triaxiality. I'm going to go over this kind of briefly. You can read my thesis if you want more information or talk or look online of many things. But the main point is Mars and every celestial body is not a perfect sphere. We're not in basic mechanical physics anymore. It's no longer a point mass. Now it's a body with imperfections, just like you and me. There's bulges, there's equators, ridges and lumps, valleys and bumps. And it can be described as the sum of the gravitational potential, area potential as we call it, and this imperfection. Here's the equation for it. So you can see your negative mu over r, that's your point mass, and then you have this phi, which is your imperfections. So how can we describe that? Well, if you actually go back, I forgot to mention, if we go back, you have those L's and M's in there under the P, subscript C, subscript S. That is used to describe the imperfections by slicing it. You can slice it vertically, you can slice it horizontally. Essentially, that function is just a way to describe the surface of the sphere, describe the definition. So you have your sectoral, which is vertical, and you have your zonal, which is horizontal. That'll just further in this horizontal and vertical. This ties directly into a big, big fact for aerostationary satellites. That's called the J22 effect. So let's make our way there. What do we care about for an aerostationary satellite? Well, let's take the divergence of that potential, and we get this long equation. Basically, what this means, it's the acceleration that the observer would see on the ground, or it's the acceleration of the eastward component of the spherical coordinate system of the spacecraft. It's the most important one because that's the one that's really going to make it move in the sky. And the dominating term is when L equals M equals 2. And this results in some work you got to do. You sit down, you work it out, and you get the J22 effect, in essence. So thanks to Jose, we have a great graph here that actually shows how the J22 effect occurs to a free-floating spacecraft. And we can see there's 4 points here where the longitude acceleration is 0. Yeah? This is where it gets fun. This directly leads into stable and unstable points. So what does that mean visually? Let's take Mars. This is the again from Jose. It basically describes Mars's triaxiality, but super exaggerated. So obviously it doesn't really look like that if you look at it, but it's exaggerated to get the point across. If we look at the stable point, it's sort of along it's above the longer axis. So a good example is you put a ball in a valley. You push it, it's going to move a little bit, oscillate a little bit, but it'll end up falling back into the middle where it belongs. If you put it on top of the hill or the unstable point above the shorter axis, you tap it, it's gone. It's essentially the same thing here. They arise from a combination of the equilibrium points, which is from the J22 and J2 effect. Okay, so let's quickly recap what we just said here. It was a lot, but let's see if we can just get it down real quick. So due to triaxiality, which in layman terms is just a combination of the ellipticity of the equator and oblateness, there exists 2 stable and unstable points. Airy meridian is akin to the Greenwich meridian. It's just a way to define longitude equals 0. We have a stable point of 168.73, or 167.83, sorry, that's incorrect, 17.92 degrees west. And then we have 105.55 degrees west, that's our unstable point in red, and 75.34 degrees east, which is also another unstable point. A spacecraft at a stable point will have no longitudinal drift compared to an unstable point. I'll say it one more time because it's super important. If you're at a stable point, you will have little to no longitudinal drift compared to the unstable point. All right, let's go over the agenda really quick. We're going to discuss and visualize drift from a ground observer due to different combinations of perturbations or force models, utilizing STK astrogator, the astrodynamics engine I used, around 2 equilibrium points. We're going to analyze eclipses by our good friends Phobos and Deimos, and Mars. Can't forget him. And including eclipse duration, patterns, and seasons. And we're going to talk about future work, and I'm also going to briefly mention reflections if you'd like to stick around for that. For the sake of time, like I said, we're going to focus on one stable and unstable point. So let's just cut out 105 and 17. They're gone. Let's focus on key questions. What do we want to answer? Well, I'll tell you what, we want to look at the evolution in terms of longitudinal drift. What's longitudinal drift? How does it look to the ground observer in the sky? And the Keplerian elements I mentioned earlier over the course of 10 Earth days. And days are Earth unless mentioned otherwise. And how does the behavior of the orbit change as each force model is introduced? Okay, let's talk about force models. So there's a couple force models we used. We used point mass. That's what we're all familiar with. Mars is just a dot. We used the area potential. I went to 21 order. Remember when we said L equals M equals 2? Now L equals M equals 21. We're going to say area potential plus third body effects from Phobos and Deimos. Then we're going to say, okay, area potential plus third body effects from Phobos, Deimos, and the sun. And finally, our full force model is area potential, third body effects from Phobos, Deimos, and the sun, and solar radiation pressure. So what solar radiation pressure, ions hit the spacecraft and makes it move. It's pretty cool. This is the full force model equation, if you're a nerd like me. And let's jump really quick into our orbital parameters. We have a semi-major axis of 20,427.3 kilometers, low eccentricity, low inclination, very close to zero RAM, very close to zero argument periapsis, and our true anomaly is just going to be depending on from the unstable point or the stable point. Spacecraft properties. We're going to assume no albedo. That's just the reflection of the Mars. That's its spacecraft. We're going to assume no fuel mass, and we're going to assume the fixed solar radiation pressure spherical area, just for simplicity. All right, are we ready? Let's look at it. Let's look at 167.83 degrees. Oh man, that's a lot of plots. I'll walk you through it though. The top left plot represents the longitude deviation from the Keplerian two-body ideal mass. What does that mean? Basically, point mass, we should expect no longitude deviation. It should be the ideal system. There shouldn't be any perturbations. And great, there is no drift, as there should be. The top right plot is just the Keplerian elements. If you see those lines going vertically, it just means it's going from 360 to 0. It's a circle. The bottom plot represents the deviation from the same ideal system, Keplerian two-body, in the X, Y, and Z Cartesian frame. And the X-axis is time. In this case, it's Earth days. And the Y-axis on the top left plot is the drift, as I mentioned. And the top right plot, it's either degrees or meters. And then the bottom plot is the perturbation amount in meters as well. All right, are we ready? Let's introduce a perturbation. Boom, area potential. Oh crap, everything went crazy. Actually, it didn't. The longitude drift is really not that bad, 0.35 at most. Semi-major axis is now starting to increase, as we expect. And the XYZ coordinate perturbations are growing. You'll notice, though, on the y-axis of X and Y, it's a kilometer of perturbations. The Z is only 1 meter. We'll keep an eye on that. Let's add area potential plus Phobos and Deimos. We're getting more oscillatory sine wave sort of behavior. Things are starting to go up and down, up and down, up and down. But longitude deviation is still secularly trending upwards. The semi-major axis is increasing just a tad bit more, and XYZ has more, XYZ has more oscillatory movement. Let's add another one. Let's add solar into the mix. Oh, wow, that's red. The oscillatory moment is kind of gone there, huh? It's a little bit less regular, still secular increase. Semi-major axis is now increasing upwards with an oscillatory movement. But interestingly, it went down. But what we're really concerned about is the full force. Now we're back to normal. We're looking at purple here. That's the full force model. And we can see we're back to our usual oscillatory program. The X and Y coordinate perturbations are at 6 kilometers. Our semi-major axis is still increasing upwards, relatively the same amount, only 8 meters, which is pretty good. And longitude deviation is now at 0.5 degrees. And I want to note really quick, perturbations are not created nor destroyed in these coordinate frames. They're simply seen in a different lens. Like if you look through to a star in different wavelengths, you get different information, right? It's essentially the same thing. But I think we can go more. 10 days, I feel like didn't tell us much. I mean, you're not going to sit there for 10 days and that's the mission. Let's go 100. Starting off with our point mass. Again, we expect no perturbations. This is the ideal system. There should be no perturbations, and there isn't. As we add more force models, things get more crazy. We're starting to see some more oscillatory movement in the longitude deviation. Semi-major axis is now going back down, and our perturbations are growing in the XYZ. As I keep adding force models, our perturbations are going to grow more and more as we expect. And at the end of it, at the full force model, we can see the longitude drift is starting to form like a wave. And semi-major axis is like half a wave, and XY are 6 kilometers, and Z is still 10 meters. I remember sitting in my chair after getting these plots and thinking, there's more to the story. 1,000 days, let's do it. 3 Earth years. This is more akin to maybe how long we can plan out some missions. Okay, we're starting off the ideal. We expect nothing, we get nothing. Awesome. Let's add our force models. Holy cow, look at that. Let's just keep adding them. Full force model. There's a lot to unpack here. Let's start with the top left, the deviation. we're seeing a still oscillatory movement, but now it's secularly trending downward. Remember it was upward at 10 days? Now it's downward at 1,000. Semi-major axis there is now kind of stabilizingly just doing a sine wave around a midpoint. It's not really going anywhere. X, Y coordinate perturbations, 40,000 meters. That's a lot. Z is only 100. That was interesting to me. That didn't make sense to me. I want to take a closer look. I want to take a closer look at that. So let's just throw it back into radial. So obviously we're just taking full force model. This is what you just saw earlier, just with just the full force model in purple. Huh, look at that. Radial perturbations are little. Even though XYZ looks intense, at the end of the day, it's like less than 30 meters. This is important why we analyze different coordinate frames, because sometimes they tell a different story than what's really going on. But let's take another closer look at the Keplerian coordinate frame and see the semi-major axis drift from that ideal scenario. So again, we have our semi-major axis in blue. That's that wave movement. And if we look at the drift, the deviation, we're at 4. Keep in mind the semi-major axis is 20,428 meters. 4 meters is really small compared to that. It highlights the stability. It highlights why the stable point is stable as it is. I mean, 4 meters is incredible. But what may be the most applicable and the most interesting is a longitude frame, aka what it would look like to a ground observer. So the top plot, as I mentioned before, is that deviation. You might be wondering why it goes downwards. That's because the point mass actually does drift. This is because that you have to have to the precision of 0.00001 kilometers to get no drift. That's just not possible. Point mass is going to have slight drift. That creates that secular downward trend. But this bottom plot is actual longitude over days. And in red is the stability point. Check that out. Just oscillates all around it. Doesn't go anywhere. That's awesome. So to the ground observer, they're looking at the sky. It's moving left and right 1.5 degrees. You point your telescope there, you're going to get it. That's the best part. So let's see an unstable point over 1,000 Earth days. You know, a stable point was great, but let's check out the unstable point. Let's check out our 75-degree friend here. Oh, man. That's bad. Longitude deviation, it doesn't even, I don't know how to describe that. I mean, it gives some really interesting shapes. The semi-major axis is no longer a sine wave. Again, it's like some weird bridge step thing. And XYZ coordinate perturbations are larger. So let's take a closer look at the longitude deviation. That blows. That's not good at all. Basically, what this bottom plot, again, is just the longitude over time is showing is that what we want to be is around that red line right there. That's where we want to stay at. What it's doing is circling Mars. It's going up to 180, back to negative 180, aka going around, it's going around, it's going around. You point your telescope to 75, you'd get it once every 400, 200 days. That's not very great. Okay. I want to move on to eclipses. This is the pretty fun part. An aerostationary satellite can be eclipsed by 3 bodies while in orbit. That's Mars, of course, penumbra, umbral. Really quick, if you don't know what penumbra and umbral means. Take the moon. When the moon covers the Earth, or sorry, covers the sun, a total eclipse, that's umbral. That's the body blocking all the light from the star or the sun. Penumbral is partial coverage. That's your partial solar eclipses. Obviously, Mars is huge. It can cover the entire sun from the perspective of the spacecraft, or part of it. Phobos and Deimos, on the other hand, these small asteroids, no way. No way they're going to cover the spacecraft, or the star, fully from the spacecraft. We're looking at penumbral eclipses. Some more key questions here. How many eclipses appear per eclipse season? And is there any apparent pattern to their eclipses? And how sensitive are eclipses to the respective orbit and force model? I want to go over some geometry situations. Again, shout out Jose for this awesome plot. These are all visually what it would look like, just top-down perspective of a eclipse site Deimos. So the dashed line right there is the aerostationary spacecraft. That's your square, and the black circle is Deimos. And the main thing to note out here is that in the A plot, that's the closest eclipse of Deimos. You're looking at an angular diameter of 0.19 degrees. What does that mean? It's small. It's super small. But it's still going to block some light. It's important to take note of it. And also, all these are symmetric or among the x-axis. Let's keep that in mind. But what does it look like in STK? That's the engine I use. Well, looks like that. About what you expect. Literally exactly what the geometries we had earlier. Let's look at Phobos. Phobos is the interior moon. And again, the dashed line is the satellite. The black circle is Phobos. And there's about 3 situations times 2 because symmetry, so 6, where that can occur. And again, angular diameter is 0.1. Pretty small. Let's take a look at it in SDK. Cool. That's what we see. Now, I actually want to go a little bit more into SDK. I've always wondered when I was getting into this stuff, what does it look like just to use spacecraft or astrodynamics tools? Well, I'll show you. It's hard to see in the room, but I'm sure people online can see. Right there in that right, Aerostat 167, that's your satellite. And that little dot right there is Deimos. And it's actually, that dot is way bigger than how Deimos really is. The dot is just a UI overlay. But that's cool. That's what it looks like from the perspective of the spacecraft. And let's look at Mars. Here's a penumbral eclipse from Mars. Again, it's hard to see in the room, but this line right here is Mars. That is a penumbral eclipse, and that's a satellite. Sometimes it feels like a video game, and I love that. Let's talk about orbital parameters and some errors. We're going to look at 168 stable point again for time. If you want to look at more, you can check out my thesis. We're going to use these orbital parameters. I won't name them out loud, but they're pretty similar. They're not exactly what we had earlier, but they're pretty close. And there's 2 notable cases of error. A fake eclipse. Let's say an eclipse occurs by the moon. And that eclipse would only occur if Mars wasn't there. So moon, Mars, satellite, aka the moon eclipse is only occurring during a Mars umbral eclipse. So if Mars wasn't there, it'd be eclipsed. It eclipsed the sun. But since Mars is there, it's obviously not going to eclipse the satellite. It's already being eclipsed by Mars. It's a mouthful. So we call it a fake eclipse, and we take care of those. We get rid of this. Double eclipse. This is interesting. I'm not entirely sure why SDK Astrogator does this, but there are some edge cases where they say that the eclipse occurs, stops, and then boots back up a minute later. These eclipses, spoilers, occur days apart. So if 2 eclipses occurring right next to each other are kind of physically impossible. It has to be the same eclipse. So we take care of that as well. All right, this plot's awesome. It's some old data, but I like to use it to showcase the actual duration difference. So on the X is date or time, and on the Y is the eclipse present. So if there's a dot, there's an eclipse occurring. And then that little box in the middle is a subplot looking at November 27th, 2025, which I guess already passed. The Mars eclipse in red occurs for 1 hour and 17 minutes. That is Phobos, or yeah, that's Phobos. That's 2 dots. You can't tell. It's super small. So sort of emphasizing how spectacularly different these eclipse sizes and differences are. Let's take some looks at eclipses by the moon. One Martian year at 168 degrees east. Our first eclipse season, 2030. The x-axis is the date, the y-axis the eclipse present. The black is Phobos and the gray is Deimos, of course. Penumbra, typo. But the numbers represent the actual duration of the eclipse. So 38, 107, 232. And then at the bottom, we have 75, 61, 57. Awesome. Thanks for attending, is what I would say if that was the whole case. But no, again, these missions are not lasting 1 Martian year. They're lasting multiple years. So 1, let's go to 5. Let's see what happens. Let's jump straight to it. Whoa. That's a lot. But what's really exciting is how many there are. The top plot is the overall view over 5 Martian years. And the bottom plot is each season. Gray is Deimos, black is Phobos. And each number represents the duration of the eclipse. And you can see that each season is drastically different. 2032 has 2 eclipses. 2038 has 6. It's incredible. And there's no pattern, at least that I can tell. Here's a little fun bit. Spacecraft operators don't use these plots. Well, they might. They use tables most of the time. This table is awesome. I love this table. The first column represents the date of an eclipse occurring, the entry and exit time, and the duration for that body, which is either Phobos or Deimos. And it shows how close Mars's last eclipse was, or after it will be, and the duration of that eclipse itself. So, for example, I always love to point out, let's see if I can get the laser pointer working here. I always love to point out this right here, 16th of March, 2037. That eclipse lasts for 68.7 seconds and it's 0.03 after the last Mars penumbral eclipse. Think about that. You're already pretty close to losing battery because of an eclipse. Maybe you are, maybe you aren't. I don't know. But that's going to have an effect. And it's cool to note that out. Okay, let's take a look at Mars really quick. Very regular, clear apparent pattern. I mean, people write papers about this. The plot on the right here shows the time on the x-axis and the duration on the y-axis in minutes. And the black lines are the umbral eclipses, the blue lines are the penumbral eclipses, and the blue dash is the theoretical longest penumbral eclipse. And you can see that each Martian umbral eclipse is relatively the same duration at the peak, and they occur relatively regularly. The left plots show the tables of these penumbral and umbral eclipses. So the top left one is the penumbral eclipses by Mars, which again isn't fully covering the sun. And it shows the beginning, peak, and ending seasons. So that basically means when does the season start and end, and when does the highest or longest eclipse occur, and the duration of all those. And the bottom left plot is the same exact table, again, showing the start and end of the eclipse, when does the peak eclipse occur, for how long, and how long the beginning and end eclipses occur for the umbral eclipses. So let's compare stable points. 168 and 342. Do we think they agree? Probably, maybe a little bit. All right. Well, we know 168. We're pretty familiar with that. That's what it looks like. Let's go on 342. Oh no. Not that well. The first eclipse both have one Phobos and two Deimos, but drastically different days, weeks apart. And the second eclipse season in the 168 has only Phobos. And the second eclipse on the other one has only Deimos. That was kind of unexpected, at least this amount of difference. Let's get rid of all the perturbations. Let's go back to basics. We're talking Keplerian. We're talking point mass. Let's choose the semi-major axis, 20,247.7. Okay, this is what we get. This is what we know. Let's plug in this very specific semi-major axis because it has no drift. Wow, that's not even close at all. So this is telling us that there's more to discover here in terms of sensitivity and initial conditions. Varying initial conditions is actually having a direct large amount of changes in the result. I'm running out of time, so I'm going to summarize this really quickly. We just talked about investigating the evolution of the orbital, frames over 1,000 days, 10, 100, 1,000. We quantify behavioral changes and adding each perturbation. We analyze geometric situations. We summarize and visualize eclipses and plots and tables, and we briefly investigated and talked about sensitivity of semi-major axis, more than likely all the Keplerian elements. So some future work. I think it would be really cool to make this into a pipeline. Well, kind of already is pipeline, but make it into a really well-made pipeline. Let's say someone's developing a mission in Jupiter, the Jovian system with Saturn, or back at Mars, and they have this orbit that they can spit it into my pipeline and it'll read out those plots. I just gave you the tables of all the eclipses that occur, which would be great for electrical engineers and thermal engineers. Like I just said before, also utilize that same automation to investigate that sensitivity we just talked about. Why, how much does it change? Why does it change, etc. would be used for that. Okay. That was the thesis, but I'd like to go to the fun part, a little reflection about my time at Ventura Community College, where I'm from, and UC Santa Cruz. My time here has been horrible. It's been papers, it's been blackboards, it's been whiteboards. No, it hasn't. That's a joke. My time here has been great. I've done systems engineering, mechanical and thermal engineering. I've been to 2 NASA camps. I've adopted a cute cat named Miso. I've done astrodynamics, which I'm doing now. I've done exoplanetary science, my first community college here at UC Santa Cruz. I did, supernova science. I did exoplanetary science a couple of years ago. Had to retire my car. I've been doing observatory. It's been great. I can't say it's been easy, as many in this room can attest, but I did it, and we did it. pointing to people in this room that are graduating with me. Um, and at the end of the day, that's all that matters is how you get it and you put your best into it. I want to do some brief acknowledgments. I want to give a quick shout out to Jose for being a great mentor and taking me on as an intern with quite literally little to no experience in orbital mechanics and teaching me that and solidifying my passion in life and giving me the opportunity to practice what I want to do and knowing that's what I really want to do. I want to shout out Natasha for single-handedly starting my academic career and guiding me all the way here, mentoring me not only in exoplanetary science I mentioned, but just life in general and helping me lay down the tracks to where I am today. I want to give shout out to David Smith for guiding me academically through UCSC for my first quarter here, giving me and showcasing me opportunities to grow my strength in aerospace through cross enrollment, as well as guiding me throughout this entire terrifying thesis process. I want to thank my family and friends that are here, Kwok and Cameron, who are very graciously decided to come. And of course, got to give a shout out to my wife, who I don't know how I would do any of this without her. She quite literally told me to take that internship actually at NASA in astrodynamics. I wasn't going to take it because I had another one and I felt bad, but she said I should look out for myself, and I did, and it really paid off dividends. So that's my presentation. I really appreciate everyone both on Zoom and in person for coming. Sorry it ran a little bit long. But I really appreciate everyone just listening to me blab about what I love and what I've been doing the past 9 months. And if there's any questions, let me know. Thank you. Really appreciate it.